All right, let's go ahead and go over this homework 12 stuff. So oxidation numbers for the cations, the anions, and then the nomenclature, so the naming for it. So which one's the cation, which one's the anion? How do you know? Hydrogen's the, why is hydrogen the cation? How do you know that? No? Metal. It's always +1 unless it's with a metal, and chlorine is definitely not a metal. So that makes hydrogen my cation, which makes chlorine my anion, and then we just said it's always positively charged if it's with a non-metal, so that makes the hydrogen a +1, which automatically makes the chlorine a -1. So that's one way you could have done it. You could have also said halogens are -1 unless they're with another halogen or oxygen, and this is not another halogen or oxygen, so then we could have said the chlorine's -1, which would force the hydrogen to be a +1. And then the nomenclature for it? Hydrochloric acid. Why is it hydrochloric? There's no oxygen. Hydrochloric acid. That's not going very well. Okay, next one. Cation is which one? Why is the magnesium? It's always a +2. It's also a metal, right? So do we understand that if there's a substance, there's an atom in a compound, that thing is now technically charged? Are we okay with that? There isn't going to be a time when the atom doesn't have a charge on it. So we'll always consider something charged. And if you're a metal, what are your options for charges? You have two options. You're either neutral, you're a 0 if you're an atom, meaning you're by yourself, or you're positively charged, because the metals can only give away electrons. So I've got a positive, all the metals automatically just immediately become positively charged. And then my sulfur is my anion. So the rule for the magnesium is what? +2. It's in column 2, it's a group 2 metal, so its charge is always +2. So that forces the sulfide to be minus S? How about -2? That's better. So then it's magnesium sulfide. How come it's sulfide and not sulfate or sulfite or something like that?
Sulfide is because they cancel each other at their 0. They cancel 0.
No, that's not why. So? Because it's not a polyatomic ion, so it's ide. If it's not a polyatomic ion, it's ide. So if it was an 8 or an ite, it would have to be a polyatomic ion, which S isn't a polyatomic ion, it's just an ion. Okay, so I have H2SO4, and so we already talked about the hydrogen needing to be a cation because it's with nonmetals. And so then I've got oxygen is going to be my anion because oxygen's charge is -2 unless it's getting messed around with, which it's not. And so in this case I've got hydrogen as a +1, oxygen as a -2, and so I've got 8 negatives with my oxygen, and I've got 2 positives with my hydrogen. And if we want to, let me add something to this. So it's H2SO4, and I've got an H and an H and an S and an O and an O and an O and an O. And the charge has to equal 0 when I'm finished with this. And we already know that the charge on the hydrogen is a plus, and the oxygens are -2, -2, -2, -2. So that gives us a total of -8 and a total of +2, but these things need to be 0. And right now what I've got is a leftover plus or -6. So that means the charge on the sulfur must be a +6 to get that to cancel out. Because that's what we're going for. How come we're looking for 0 in this particular one? It's a molecule, it doesn't have a charge, so it needs to make sure it's 0. So then I've got S, why does it keep switching? S with a +6 charge. Okay. Oh, and what's the name of this thing? Oh, it's weird how it's moving that thing, but sulfuric acid, right? How come not hydrosulfuric? There's an oxygen there, so I don't get to use the hydro prefix. Okay, so the next one, I've got an I and an O. Which one of those is more electronegative? The O. It's the second most electronegative one, right? So unless it's with fluorine, it's always going to be the most electronegative thing in a compound. So I'm going to make oxygen over here and iodine over here, and the oxygen's a -2. How many -2s do we have? So that's a total of -8, right? How many what charge do I have to have left over? -1. So I have to cancel out 7 of the 8 negatives. So then the charge on the iodide is +7. It's pretty straightforward with that one. +7. And what is this thing called? Periodate? Are we okay with that? Iodate is IO3 negative. Add one more oxygen and I call it periodate. Okay, and so manganese is a metal, so that means it's got to be the cation one. And so iodine's over here. That's terrible looking. Why does it keep doing that? So the iodine's charge is a -1 because it's a halogen. So that makes the manganese's charge what? +3. And so the name for this? Why is it manganese 3 iodide? That's the oxidation state for the manganese, so you have to tell somebody that. Why do I have to specify that it's manganese 3 oxide, iodide? Nope. Because it's a transition metal with multiple options, multiple oxidation states. If I just wrote manganese iodide as the name, what formula would you pick? You wouldn't know what to pick, right? Because manganese has lots of different options. So you have to physically state which one of the options it is. How come I didn't have to do that with the magnesium? Because there's only one option. So I didn't have to say magnesium 2 because it's always 2. I do have to say it with the manganese because the manganese has like 7 different possibilities. Okay. If a molecule is polar, what is occurring, and what types of molecules can be polar and which cannot? So what molecules can be polar? Or sorry, what's occurring in a polar molecule? Say again? How does that happen? So we want to put that together in one phrase? I like what you said, mixed with what he said, so. It's due to a larger electronegativity, but what is actually happening?
Uneven sharing.
Perfect. Uneven sharing of electrons. It's sharing, right? It's supposed to be sharing, but it's an uneven sharing. So it's a sharing of electrons. So since it's a sharing, what type of molecules can be polar? And which cannot? Covalent has sharing of electrons and ionic has transfer. There isn't any sharing of electrons, so I can't have uneven sharing. Okay. So I want to draw the Lewis structure, the 3D model, and if applicable, a 3D VSEPR structure. Also name the structure. So for the first one, I've got a carbon, and then there's going to be 4 electrons for that, and then 3 times 1 for the hydrogens, and then 7 for the fluorine. So I have 14 electrons to deal with. Are we okay with that? Carbon's in 4A, hydrogen's in 1A, and fluorine's in 7A. So that gives us our 14 electrons. Who are you going to put in the middle for the structure? How come? It can have up to 4 bonds. And what about the hydrogen and the fluorine? They can only have 1 bond, so I cannot put them in the middle. They are always going to be on the outside. So I'll put a carbon, and then a fluorine, and then a hydrogen, and a hydrogen, and a hydrogen. So for my Lewis structure, I have used 2, 4, 6, 8 electrons. I have 14 to use. So is anybody happy? The carbon and the hydrogens are already happy, right? So the only one that's unsatisfied is the fluorine, and it's seeing 2 electrons. It needs to see 8, but luckily I've got 6 leftover electrons. So then I can put a pair there, and a pair there, and a pair there, and it's happy. So there is my Lewis structure. What's my what's the shape of this molecule? Why is this tetrahedral? Got 4 atoms around it, right? There are no lone pairs of electrons on the central atom. There are lone pairs on the molecule, but they don't matter for the shape. The only thing that matters for the shape is if the lone pairs are on the central atom. So then this thing is going to be, I'm going to flip it around a little bit. I'll put the chlorine or carbon there, and then I'll put the fluorine on top. And then I'll have a hydrogen over here. And then I'll have a hydrogen come out. And I'll have a hydrogen go back. So there's my 3D structure, and I didn't ask this question, but is this molecule polar or nonpolar?
No. It would be polar.
How come? Yes, it's polar. Why?
Because the fluorine would be pulling.
Yeah, what's the electronegativity on the fluorine is like 4, right? And on the carbon, it's 2.5. So then that's a 1.5 difference in electronegativity, which means the electrons from the carbon are going to get pushed up to the fluorine, which makes this side of the molecule partially negative and this side of the molecule partially positive. So is this going to mix with water? Yes, water is polar. What will this not mix with? Oil, gasoline, acetone, WD-40, anything that would be nonpolar. Okay, so now we've got this next one over here. So I've got the nitrogen has 5 electrons plus 3 times 7 electrons for the iodine. So that gives me 26 electrons to deal with, right? Who are you going to put in the middle? Why the nitrogen? Give me a couple of reasons. One, it's not like the other, it's the odd man out. I wouldn't know which of the 3 iodides to pick if I were going to put that in the middle. So put the other one that's by itself in the middle. And what's the other reason I can't put an iodide in the middle? It can only make 1 bond. It's in the halogen column, so I can't have it in the middle because it can only hook up to one thing. All right, so I'm going to throw my nitrogen in the middle. And then I'm going to put an iodine and an iodide and an iodide. Is anybody happy? Nobody's happy. I've used 6 of my 26 electrons. I still have to deal with 20 more electrons. So what I'm going to do is I'm going to tack a couple of electrons pairs around that iodine, and he's happy. And I put them around this iodine, and that one's happy. And this iodine, and that one's happy. So are we okay with the iodines being all happy? How many electrons have I used so far? 24. So I still need 2 more. And that's good because my nitrogen is not satisfied, correct? So what I'm going to do is I'm going to throw 2 electrons right there. And now everybody's happy and all my electrons are used. Okay, so I have to come up with a 3D structure for this. And there's going to be a couple of structures for this one. So nitrogen with a pair of electrons up top and an iodine here and an iodine here. Oops, and I wrote H. Iodine there and an iodine there. So with the electrons, what shape do I have? I have a tetrahedral shape. Without the electrons, what shape do I have? Trigonal pyramidal, right? This is not flat. If you forget to include those electrons on the nitrogen, then what it looks like is a central atom with 3 things on it. And so that would make you think that it was trigonal planar. But this is not trigonal planar. And the difference is, if it was trigonal planar, it would be nonpolar. But since it's not trigonal planar, it's got a vertical shape to it that makes this molecule polar. So if you don't know how to draw the Lewis structure and you don't recognize that the shape is 3-dimensional and not 2-dimensional, you're not going to be able to answer the question, will this mix with water or not? There's a difference in electronegativity between the nitrogen and the iodine, so there is going to be electron movement, and so this is going to be a polar molecule. So the 2 shapes are tetrahedral with the electrons, right? And then the shape of the molecule itself is trigonal pyramidal. Why am I calling it trigonal pyramidal? Why am I just not calling it pyramidal?
Because there's 3 players.
And pyramids are supposed to have 4 sides, right? Strictly speaking, if you say pyramid, it's a 4-sided 3D figure. This is a 3-sided 3D figure, so it's trigonal pyramidal. Okay, I think that's it. Yep.